So yesterday we looked at finite series where it stopped after a certain number of terms. Today we're going to look at infinite series, which is going to require you to remember how to take some limits as things approach infinity. So we're going to do a quick little refresher here. If you do the limit as n approaches infinity of this function, which happens to look like some of our summation formulas, you would probably want to multiply some things together. So if you do a little bit of multiplication, and enjoy rewriting that limit notation like 500 times today, you end up with 18n squared plus 18n over 2n squared. You could use L'Hopital's rule, but I'm just going to divide that up into two separate fractions because it simplifies nicely if I divide 18n squared by 2n squared into 9. And if I divide my other two terms, it'll just divide out to 9 over n. So if you take that limit as n approaches infinity, that second term is going to get towards 0, and you just get 9. So taking limits is a big part of finding sums for infinite series. All right, same idea, just a little bit messier. So I'm going to multiply that n plus 1 times itself while I'm rewriting. N squared plus 2n plus 1. And then multiply things together. You're going to end up with the limit as n approaches infinity of n to the fourth plus 2n cubed plus n squared all over 4n to the fourth. And again, could use L'Hopital's, but let's just split those up because this is going to work out nicely. You'll end up with, if you divide those, just 1/4, and then plus a 1 over 2n. And a 1 over 4n squared. Those last two terms, if n's getting larger and larger and larger, are going to go to 0, so you just end up with 1/4. Okay, so you can find limits. You're saying, hey, where are the sums that we talked about yesterday? Here they are. So we're going to find the result of this sum as the number of terms in your series approaches infinity. So if you let this series continue on forever and ever and ever, what would your sum add up to? So I would start by going ahead and simplifying a little bit. So multiply and square your I over n, and then I'll go ahead and multiply it by 1 over n to make it n cubed. So the only thing that's changing as you go through this sum term by term is your index I. N's a constant, so I'm just going to factor that 1 over n cubed out. And then you'll be left with 1 over n cubed times the result of that sum, which we have a formula for that we talked about yesterday. So let's write down the formula for what that sum would be, which is to the second power, so that'd be your n times n plus 1 times 2n plus 1 all over 6. And then we could multiply that times our 1 over n cubed. And if we take that limit, that's what this series is going to add up to if we let the number of terms continue on forever and ever and ever, because the terms basically get smaller and smaller and smaller. I'm not actually going to multiply the top together. You'll notice I just wrote other stuff there. That's because all of the rest of those terms are going to have smaller exponents, so the denominator is going to have like a variable left in it if I divide. So they're all going to go to 0, and the only term that's not going to be 0 if you take the limit is that first one, which is just going to give you 1/3. Sorry, that was kind of fast. Oh, my iPad decided it would be silly, so I had to zoom in and out a couple times. Okay, here we go. So same idea. Go ahead and simplify your expression inside your sum. So I need to take 1 plus k over n times itself here. And do that real quick. Gets me that. And then I'm going to multiply that times my 2 over n. And rewrite this sum with everything that's a constant factored out is kind of our overall game plan. So if I multiply that together, distribute my 2 over n, I've got 3 terms in this sum. Let's split them up and factor out our constants so that we can use our summation formulas to get the actual result. So 2 over n is a constant, so if I factor it out, it's just times 1 there. Copy and pasting for once. I can factor out 4 over n squared, and then that's just going to leave me with the sum of k, so just consecutive integers to the first power, and then factor out 2 over n cubed, and then I've got the sum of a bunch of perfect squares. Okay, use your formulas for your sums. So if I take my factor that I factored out, 2 over n, if I add up a whole bunch of ones, I just get how many ones there were, n, so that's that. Formula for a bunch of consecutive integers to the first power is there, and the formula for adding up perfect squares, thanks Twitter, sorry, throwing notifications up that you can't see, I realize, but it's fine, is gonna be like that. All right, if you take the limit of that sum, a whole bunch of things are going to simplify, or they're going to have a value of 0 as you let n approach infinity. So again, really kind of, if you want to avoid a bunch of extra work, you don't have to fully multiply it out. So your highest degree term is going to be the only one that value does not go to 0 as n approaches infinity. So I'm going to end up with 2, and then another 2, and then a 2/3, so I get 4 2/3. This one we have to do the whole thing. We have to write a formula for our series, and then we have to figure out what it adds up to. So if I was to add up all these numbers, a whole bunch of perfect cubes, divided by our value to the 4th power, it's gonna look like a whole bunch of perfect cubes, so that's changing. My index is k to the 3rd. And then I can factor out a 1 over n to the 4th. We haven't used the formula for the sums of perfect cubes very much, so we're going to use it now. It's just the one for your integers to the 1st power squared. I like that. Makes it easier to remember. And if you were to think about actually multiplying that out, maybe not all the way, but at least squaring it, makes it a little easier. You'd have n squared and n plus 1 squared, and I always forget to square the denominator, so don't forget that. You'd end up with 4. Whole bunch of terms on top, but really the only one that matters is n to the 4th. Divide it, and you get 1/4.